Hello, my name is Agni Pratham and I am part of Group 10 of PH421 2023. Our project is titled Spontaneous Parametric Down Conversion for Quantum Applications. My teammates are Spandan, Aniket, Aditya, Nahush, and Siddharth. Before we begin, let me give you a short introduction on our project. Spontaneous parametric down conversion is a vital quantum optical phenomena with a lot of applications in different areas of quantum information and technology. It is a process that basically refers to the phenomena where we have an omega 3 photon spontaneously break down into two constituent omega 1 and omega 2 photons. The word spontaneous indicates that we do not have any other factors to facilitate this phenomena, and the word parametric indicates that we have parameters that we can adjust to modify how we receive the output of this. For example, we tune the intensity and power of the pump wave, etc. Right? So this phenomena has a lot of applications in different areas of quantum technology, and we'll start by understanding it from the basics. Let me take you through the theoretical derivation of SPDC by considering the classical case. We consider the classical model of electromagnetism where every solid is made up of constituent charges which are displaced from their position in the presence of an electric field. Right? So we have a dipolar type of interaction when we have an incoming electromagnetic field at some frequency omega. We then evaluate how these charged particles are moving around in the presence of this field. To achieve nonlinear effects, we consider a centrosymmetric potential, which is U equal to half kx square plus 1 by 3 max cube. When we plug this back into the equation of motion, we can see that we have an extra ax square term, which basically causes the equation to go from linear to nonlinear. This gives rise to all sorts of new interesting effects that lead to the changes that I was mentioning earlier. Okay, so, on manipulating Maxwell's equations, we arrive at the optical wave equation. This is of interest to us since we can obtain the amplitudes of input and output waves by working on these equations when examining phenomena such as wave propagation inside a nonlinear crystal. The equation is as follows: del square E minus 1 by c square del square E by del t square minus epsilon naught c square del square P by del t square. Note that this P over here is the polarization which consists of both the linear and the nonlinear polarization. And SPDC is a second order nonlinear phenomena. Therefore, we consider all these terms up till one nonlinear degree, which is basically the second order. The first nonlinear polarization term we get is Pi of NL, which is basically summation over J and K, chi ijk, where chi is the second order susceptibility tensor ejek times epsilon naught. In our process of down conversion, fortunately enough, we still obey the principles of energy as well as momentum conversion. So we have h bar omega 3 equal to the sum of the resultant two photons, h bar omega 2 plus h bar omega 1, and we have our momentum vector being conserved because momentum p is equal to h bar k. These are the phase matching conditions, and we actually get to learn later on that we want these conditions to be satisfied to achieve optimum efficiency of our output. To solve these differential equations that I have outlined here, the optical wave equation to be precise, we will consider an ansatz of the following form, where we basically consider the electric field to be made up of constituent waves at particular frequencies, right? So EI is just AI into e power k iz minus omega it plus the complex conjugate to ensure the reality of the wave. And note that k is always n omega by c, and the square of the refractive index is the first order susceptibility, right? So naturally, when we assume electric field to have such a form, it enforces a constraint on the form of the polarization as well, which is the same constraint that the polarization is also made up of a bunch of sub polarizations which are each at their own frequency. And since we are concerned with observing different waves along with their different frequencies, we convert our optical wave equation from a time domain 1 to a frequency domain 1 by basically taking its discrete Fourier transform. And the way we do this is that we substitute the electric fields in as a summation of their constituent frequency fields. Now, after we do that, the form that just comes out on its own is where we have an omega square in the denominator of the second term, as well as in the numerator of the second as well as the third term. That is because when we have a del square del t square with respect to all these e power I omega terms, we end up having an omega square pop out, right? And after we do this, we substitute our ansatz into it, keeping in mind that we have a slowly varying envelope approximation, which basically tells us that the envelope of the wave that we are considering varies in a very slow manner. And mathematically, this translates into us being allowed to neglect the second derivative of the amplitude with respect to the wavelength of the wave, right? So when we have this del square and we substitute the form of E into it, we end up neglecting the del square term. And as a result, we get a very neat differential equation directly for the amplitude of the wave. So you can see that we have 2 ik3 dA3 dz equal to minus 4 d effective omega 3 by c square a1 a2 e power I delta kz, right, where delta k is the phase mismatch term, k1 plus k2 minus k3. So what I can do here is that I now want to look at how my resultant intensity varies with my only parameter, which is delta k. So what I do is that I complete the integration. So I have e power delta k. So I complete the integration. I set the lower and upper limits to be 0 and L, which means that the beam has basically come out a crystal of length L. And then I have a formula which is I3 is equal to 2n3 epsilon naught c mod a3 square. So after considering all of this, I get one big formula which basically graphically looks like this. And here we can clearly see that we want delta k equal to 0 for maximizing our output. When phase match is perfectly achieved, we have the maximum amount of intensity of our output wave. This is what we want to achieve. But note that this is not always possible, because when we have ordinary crystals, we have n1 of omega 1 being less of n2 of omega 2 being less of n3 of omega 3 for an increasing set of frequencies, because this is the condition of ordinary dispersion, right? We want birefringent crystals because they might possess, I mean, they do possess two or three different refractive indices, where we take advantage of the presence of the ordinary and extraordinary direction, because then we can phase mismatch, we can obtain phase matching perfectly along two different directions, right? This will be discussed in full detail in by my partners in the coming sections. But the idea is that along one axis you cannot equate n1 omega 1 plus n1 n2 omega 2 equal to n3 omega 3. But if you consider one half of this equation to be from the extraordinary dimension and one from the ordinary dimension, then an equality is possible, and this is what we take advantage of, right? So what I will show you in this part is why a classical model is not feasible. It's quite intuitive, really. When we evaluate the differential equations for a1 and a2 using the same equations described earlier, we end up with the following equations, which is basically a coupled differential equation system. Once I solved this by writing it in matrix form, diagonalizing the operator, and converting it to a stationary basis and figuring out the general solution. This is the general solution obtained for a2 of z and a1 of z. What we notice here is that the second I set a1 of 0 equal to 0, both a2 of z and a1 of z automatically become 0. This is a problem because the spontaneity of SPDC implies that the phenomenon must happen on its own. Omega 3 wave must break down into omega 1 and 2 even if there is no omega 1 present with it initially, right? So that is why there is the spontaneous in SPDC. But clearly, from the classical derivation, we see that this is not possible. This is what sets up the setting for the next part of the project, where we discuss how to explain this phenomena using quantum derivations. Moving on to the next section.
So, I'll quickly go through the derivation of quantized EM field. To quantize electromagnetic field, we start with Maxwell's equation, that is del cross E plus dou B over dou T is equal to 0 and del dot B is equal to 0. We then use Coulomb gauge, that is del dot E is equal to 0, which results in B is equal to del cross A and electric field as minus of dou A over dou T. Once we make these substitutions, we get making these substitutions in the first expression, we get del square minus 1 over c square, dou square over dou T square into A is equal to 0. And the solution of this is given by A into e to the power iota k dot r minus omega t plus complex conjugate. That is the plane wave solution. And also omega is equal to kc. And uh, we can see that the divergence of A is 0, which implies that k dot e is equal to 0. So once we take divergence of this, we'll see that it simply becomes equal to k dot e is equal to 0. So suppose we put our electromagnetic field in a box of volume LQ and having periodic boundary conditions. So later on, we'll take the limit of L tending to infinity. So for now, if we take finite L, we can say that K forms a discrete set. So Kj is equal to 2 pi Nj over L. Nj is belongs to integer and J is 1, 2, 3. So basically each component of K forms a discrete set. So after that, we write a vector polarization as summation over K comma lambda into a k comma lambda e to the power iota k dot r minus omega t plus complex conjugate e k comma lambda. And lambda here denotes two possible directions of polarization for each of the wave vector. So lambda can be 1 comma 2. Uh, After that, the classical Hamiltonian for an electromagnetic field is given by half of epsilon naught modulus of e square plus 1 over mu naught modulus of b square into integration over whole space. That is equal to, we substitute for electric field and the magnetic field. So we write electric field as minus of dou A over dou T, and we write magnetic field as del cross A. So once we make those substitutions, we get half of epsilon naught dou A over dou T square plus 1 over mu naught del cross A modulus square into d cube r. And we can simplify this using Parseval's theorem, which simply relate the function and its Fourier transform. So modulus square of function into dr, that is equal to summation over k modulus of fk whole square. And once we make these substitutions and simplify the expression, we finally get Hamiltonian as 2 times epsilon naught summation over k comma lambda omega k square into modulus of a square. And we can split modulus of a square as modulus of a comma lambda real part square plus modulus of a comma lambda imaginary part square. So since a k comma lambda t can be complex, we can write it as uh, some real part into imaginary parts. So basically a k comma lambda into e to the power minus I omega kt. So once we do that, uh, if we take derivative of real part of a with respect to time, we find that it is equal to omega k into imaginary part of a. Similarly, if we take time derivative of imaginary part of a, we find that it's equal to negative of real part of a. And dou h over dou a real is 4 times epsilon naught omega k square into real part of a. And using these above expressions, we can write the real part of a in terms of the time derivative of imaginary part. Similarly, we do for imaginary part of a, and we can relate it to time derivative of real part of a. So after that, we define these variables. Let q k comma lambda be equal to 2 times square root of epsilon naught a into real part of a, and let p of k comma lambda be 2 times omega k square root of epsilon naught imaginary part of a. So Once we make these substitutions, we can see that rho h over rho q is minus of time derivative of p, the partial derivative, and rho h over rho p is q dot of k comma lambda. So basically, these resemble Hamilton's equation of motion. So we can consider p and q as conjugate variable. So once we do that and also substitute for p and q, we see that Hamiltonian becomes, it looks similar to that of a harmonic oscillator. So we can now promote p and q to operators, and we can define ladder operators as follows. So we see that the creation operator is square root of h cross over 2 omega k into omega k q hat minus iota p hat. Similarly, we define annihilation operators. And once we make these substitutions, and we finally get our Hamiltonian to be equal to h cross omega k into creation annihilation operator plus 1 by 2, uh, which is very similar to the quantized harmonic oscillator. So basically, this is the quantized free radiation Hamiltonian.
Right. So let's talk about the actual theoretical derivation of SPDC in quantum case. So earlier Agni has explained you how do we derive so in classical derivation is not able to explain the SPDC, and that is because in what happens is we want an input beam of pump, and we want to convert it into a signal and idler beam spontaneously. By spontaneous we mean that we do not give an signal input at the start. So in classical case, in difference frequency generation, what we were doing is we were, along with a strong pump, we were also giving a signal at the input. But if that signal was zero, then everything just became zero and it couldn't explain this SPDC phenomenon. So now we have to rely on quantum optics to explain this phenomenon. So in SPDC, the idler and the signal beams spontaneously appear without any input. Like they just appear directly, and the pump beam just disappear directly. So now we'll talk about photons. So to explain this phenomena, we need to quantize the electromagnetic field, which is basically we need to see this electromagnetic field as photons, as those energies we want to see as packets. So to Aditya has explained you how do we quantize this electromagnetic radiation and like derive the free Hamiltonian free radiation Hamiltonian from it, and we will apply the same here. So what we'll first do is instead of working with electric fields, we'll work with vector potentials, which will be more convenient for us, and in the Coulomb gauge where the divergence of A is zero. So this vector potential operator, we can write it as this thing. So this we can do earlier in Aditya's derivation. We have derived the creation and annihilation operators, and they are being related to the vector potential itself. So we can write this vector potential in terms of creation and annihilation, and we can create its operator correspondingly. So this A dagger and A are the creation and annihilation operators of a quantum of energy. So basically, what we do is break this electromagnetic radiation into different modes. This L corresponds to each of this mode, and for each of the mode, we associate a harmonic oscillator to it, which has an energy h cross omega L to it, and the classical beam has an amplitude of EL. This is the classical beam's amplitude. And this epsilon L is the direction of the vector potential or direction of the electromagnetic radiation. And these are the corresponding operators, and K and R have the usual meaning. So this creation and annihilation operators, what they do is they just create a photon and destroy a photon. So if it acts on a zero L, that means there is no photon in the mode L. If we act a dagger of L on this, then we create a photon in the Lth mode. And similarly, we can destroy a photon in the Lth mode using the destruction operator. And the quantized free radiation Hamiltonian, which we have derived earlier, can be written in this form. And in this, NL is the photon number operator. So basically, A dagger and A, if we act on a state, it So in case of a harmonic oscillator, it gives a factor of this destruction operator gives a factor of root n, and this a dagger gives a factor of root n as well if we act on a state, and we get an factor of n. So that represents the mode in which the nth excited state of the harmonic oscillator, and corresponding in the case of electromagnetic radiation, it gives the number of photons in that mode itself. So this operators, when it acts on a state, it will give me the number of photons in that lth mode. So in this SPDC phenomena, we can write the interaction Hamiltonian in this format, where kappa is defined is a factor, and AI, AS, and AP are the idler, signal, and pump beams creation operators and destruction operators respectively. And we have a phase factor of e raised to I delta kr minus I delta omega t, where delta kr is the basically the phase matching, and delta omega is basically the omega p minus the idler and signal omegas. So, so if we analyze this Hamiltonian, the first term represents some frequency generation where A and AS are getting destroyed and AP is getting created. That means pump is being created and AI and ARS are getting destroyed. And the second term is the term which we are interested in which the pump is getting destroyed and AI and AIS are being created. And we will work in the degenerate SPDC where in omega I and omega S are same. So basically, we create twin photons. So let's describe this situation in quantum mechanics. Now we'll visualize this situation in QM. So basically, what our wave function is comprised of three quantities, which is the number of photons in singular, idler, and pump beam. So instead of like now electromagnetic radiation, we are now thinking in terms of photons. So number of photons is the parameter that we have, and this is the any general state that we have. So initially what we have is no signal and idler beams, right? So we have zero photons in signal and idler, and n, let's say n photons in pump beam. And this is our initial state. Then we act upon this interaction, then the interaction Hamiltonian acts upon this state, and this state evolves into some state. So to find that evolved state at time t, we apply this time evolution operator using unitary operator and all, like basically just solve the Schrodinger time dependent Schrodinger equation, and we will get this state at time t is equal to e raised to 1 by I h cross integral of the Hamiltonian with respect to time, and times the initial state. And here we are also employing delta omega is 0, that idler and singular idler or singular beams are half of their frequency are half of the pump. So in that case, the Hamiltonian is has become time independent. It has become time independent, and we can substitute this here. This CC is complex conjugate, and we will let that when this kappa times t is much less than 1, we can use Taylor expansion, and we will get that psi of t is c times the initial state plus kappa t times c times this operators acting on this initial state. And then if we substitute these if we act upon these operators in this initial state, this will just give us 0 because they are destroying already what is 0, and this will give us some new state where idler and singular are being created, so it increase the number of photons increase by 1, and pump is being destroyed, so it decreases by 1. So psi at time t will be a combination of input 1 and the one where in the state which we are in interested, which is there is signal and idler beams coming out, where the one of the pump photons is being destroyed. C is just the normalization factor. So here we can see that the measured electromagnetic intensity, denoted as ISPDC, is directly proportional to square of the probability amplitude represented by the wave function. So if we do mod square, then what it gives is that the probability of being it in that state. So if we do mod of this coefficient square, then we'll get the probability of being in the state which we are interested, and this probability of being in that state is directly proportional to the intensity of that beam itself. So this wave function basically characterizes the likelihood or of being in SPDC state. SPDC state is the one where signal and idler photons are being created and the pump one is destroyed. And consecutively, the phase matching condition also is evident in this expression, as we can see there's delta k in this expression. And unlike the second harmonic generation, this exhibits a linear relationship with respect to power of pump beam. So in second harmonic, it was not linear, but in this case, what how can we see that it is linear? We will assume that the pump is very strong and it can be approximated as a classical field. So we will not use the AP operator, and we'll just substitute the classical electric field there, and which will result in it being directly proportional. So basically, instead of this, there is just EP, and then if we substitute this Hamiltonian here, this EP will just get outside, and there will be a factor of EP right here, just beside the SPDC state. And if we do mod psi square, then that gives us the EP square, and EP square is directly proportional to intensity of the pump beam. So intensity of the SPDC which we are interested in is directly proportional to intensity of pump, and that gives us the linear relationship, which is unlike the second harmonic generation. In SPDC, a single pump gives rise to two photons and one in each mode. So right, so in one mode there cannot be more than one, but those modes can be degenerate. So making this dependence clearly linear, even though there's the non-linear nature of this process. So it's also worth noting that the coefficient of SPDC state which we are interested is significantly smaller because of the factor kappa times t, that is much less than 1. So that means if we do mod uh, coefficient square of for the SPDC state, it is much less than the initial state itself. That means most of the beam is just initial beam only, and only a small fraction of the pump beam is being converted into signal and idler, which basically tells us that there's a lot of inefficiencies there, and efficiency is very low for SPDC, and that is one of its major drawbacks. Also, we have only considered two terms of its Taylor expansion. So if we have a very strong beam, even stronger than this one, AP is approximately even stronger pump, then higher order terms will come into play, and these higher order pumps will give rise to such states in which there are multiple pairs of photons being created. So here only one pair is being created. We can create more number of pairs of photons. So if you don't want that to happen, then we have to restrict a little. Like we have to get an upper bound of the pump beam, because we might think that if we just keep increasing the pump beam, then we will get more probability of getting SPDC, but we can't do it if we want to avoid generating multiple pairs. Also, in practical quantum optics experiments, there's a technique called coincidence measurement, which is employed to detect SPDC photon pairs. So, what this does is there are two detectors which are there for detections on these two beams, signal and idler, and they detect within 10 nanoseconds. That signal and idler are being detected within 10 nanoseconds. That is being detected, and this approach, what it does is it eliminates the contribution of vacuum state, which is the initial state itself, because initial state will only detect once and it won't be counted. So basically what we are doing by performing this measurement, we are basically collapsing it into the state which we want, and thus it will focus on what state we want, and then we can uh, measure it. Also, one observation was made by Mandel. It is that the number of SPDC pair events created must not exceed the number of incoming photons. So, if there are like two photons, then only two pairs can be created. And we are assuming that each incoming photon is converted, like they are being converted, and without the higher order effects. So, in conclusion, this SPDC in this way can be explained to quantum formalism only, as classical formulation cannot explain this. Now I will pass to Spandan, who will explain the further topic. Thank you.
So, hello everyone, I'm Spandan and I'm here to explain about phase matching in SPDC. So, I would like to first explain a concept called beam walk off. So, what happens is that in general, in an anisotropic medium, the wave vector k and the Poynting vector s are not parallel to each other. Because of this, we find out that the direction of energy flow and the direction of k vector, which is the direction in which the phase velocity is, are different, and this causes the interacting beams to walk away from each other. So this is one of the phenomena which is observed in SPDC. So moving on to phase matching in SPDC, where SPDC is a process in which a single pump photon splits into two photons. One is the idler photon and one is the signal photon. So this process is generally of two types. One is type 1 and another one is type 2. So when type 1 phase matching occurs, what happens is that the signal and the idler beam have the same type of polarization, such as ordinary or extraordinary. So one of the concepts in this is that at the start, what happens is that when the angle is equal to 0, so angle here refers to the pump angle, which is the red line here. So when the pump angle is 0, we find that the signal and the idler beams, uh, the wave vectors for them cannot add up to give us the pump wave vector, and because of this no down convergent light is observed. Now when we move on to and finally just reach the phase matching angle, as we can see in figure 2, what happens is that the uh, idler wave vector, the signal wave vector, and the pump wave vector, all of them align in a single line, and we observe collinear phase matching. And now, when we increase the pump angle by a bit more, we find that these three cannot match each other in a straight line, and hence they match each other at an angle. So this is what we find in non-collinear phase matching. And similarly, as we keep on increasing the angle, the angle of the photon beam, we find that the angle between the signal beam and the idler beam also keeps on increasing. So here, as we can see, the signal and the idler beam are completely, you could say, equivalent. So we can easily replace the signal by the idler and the idler by the signal, and this results in uh, us getting a cone of light which consists of the signal photons and the idler photons, and this cone of light is what expands in the distance. And afterwards we move on to type 2 phase matching. So in type 2 phase matching, what happens is that the signal and the idler beams have different polarization. So one is ordinary, the other is extraordinary, and because of that, we find that as you can see in the diagram, one of the wave vectors lies on an ellipse while the other lies on a circle. And because of this, at the angles the procedure followed is nearly the same as in type 1, but one major difference, as you can see, is that the angle between the signal and the idler beam is much more uh, larger between them as compared to in type 1. And because of this, both the type 1 and type 2 beams uh, differ in the fact that the type 2 beam we get two cones, and both of these cones walk away from each other. As you can remember, in the type 1 beam, as both of them are identical, the cone formed by both the signal and the idler beams is the same. And but in type 2, both of these cones are different. So as you can see that the black uh, vector forms some cone here in this plane, while the gray vector forms another cone, and both of them are very different. So this results in us getting two cones of light which continue to move far away. And as we will see further, that due to this reason, the both of them have two intersecting points, and we find that at these points the two photons present are in a state of entanglement, so that if one of them is found to be uh, ordinary polarized, then the other must be extraordinary polarized, and vice versa. So now handing over to my other teammates. Thank you.
Hello everyone, I'm Siddharth Stephen, and in this part of our photonics project, SPDC, we look at practical application, how it actually works in the laboratory, by taking the example of a BBO crystal, a beta barium borate crystal. So, like we saw before, practically we need to look at conditions like phase matching for efficient signal generation. So, you see here, yes, delta K, which we saw earlier to be uh, K1 plus K2 minus K3 or Ki plus Ks minus Kp. It needs to be needs to vanish or as close to vanishing as possible. So in isotropic materials or natural materials, it's hard to fulfill the condition for phase matching. So we see here Ni and Ns corresponding omegas can't be less than the pump factor index. So we have to go to birefringent crystals. These are anisotropic crystals which have different properties in different directions. So we can have uniaxial or biaxial crystals which have increasing uh, variation along different axes. Here, particularly, we look at the variation in wavelength of the refractive index. Uh, we can see the variation, the complex variation of NO and NE of the refractive index with lambda here below. We will see the data. Also, we want to achieve non-collinear phase matching so that the directions of the three spatial waves are spatially separated so that we can easily detect them after they come out of the crystal. We're using beam splitters and detectors. So for that we require non-collinear phase matching. Yes, so the wave vectors in different directions. This makes our theory more complex, but practically this is feasible. Sorry. Now we yes, beta barium borate is our crystal here. It is a uniaxial crystal with negative birefringence. This means that Ne will be less than No. So a high refractive index means a lower speed of light in that direction. So you can see that uh, which means that Ne, which is in the direction of the optic axis, will be less than No, which is perpendicular to it. Yes. Okay. And BBOs again can be used in a wide range of wavelengths. Just given here. And the refractive indices of BBO, in this case, are given by the so-called Selmayr equations for type 1 SPDC, that is from extraordinary to ordinary and ordinary for the nicer waves. We have these equations which are complex enough, and this is sufficient for achieving phase matching. With phase matching, when mixed with the chromatic dispersion, this lambda is given. Then we also have this variation of Ne and NO with theta. NO, as we know, will stay constant with the difference in theta, but N will change with theta as given by this equation, ellipsoid equation. Uh, also, uh, okay, for BBO, since it's negative uniaxial, phase matching can only occur with the extraordinary beam. So these are the two types of phase matching that we have: extraordinary giving ordinary plus ordinary, or type 2 extraordinary giving mixed E plus O, and E gives O plus E. And again, how can I say? The extraordinary index will be different for different angles, contrasting to in contrast to the ordinary index. Yes. The plot below represents the two curves. I've plotted here the variation of refractive index for BBO with wavelength. Here This is the extraordinary wavelength, and this is the ordinary wavelength. I also plotted a particular case I mentioned here of 31.7 degrees. Uh, we can use this to let's say pick the ISO lines to calculate phase matching conditions. Wavelength required for phase matching. So if we go on up, yes, we take a look at a simple case of phase matching in which the pump is at 400 nanometer and the other two are degenerate and at 800. Again, yeah, we have the degenerate uh, signal and idler beams. So for that, theta equal to 31.7 is the right spot. We have phase matching here. This is a simple case uh, for say non-degenerate cases. We need to work in spherical coordinates. There will have lots of parameters. This is the we have our energy conservation equation and our momentum equation, and from there we get 9 parameters, 3 is for the wavelength, angles, and yeah, phi and theta. So lambda we can set, and after eliminating, we have 3 parameters which we have to determine for achieving phase matching. So calculations for type 2 SPDC in with bound 405 nanometer and 810 degenerate photons, we get a walk-off angle of 3 degrees between the ideal resonant waves. So where figure 3 is an experimental result of this specific case we have here. Uh, these are the different extraordinary and ordinary photon beams with perpendicular polarizations. This is just a cut of the SPDC, and we look at some particulars of these two waves. Like they're separated both temporally and spatially, of temporal and spatial walk-offs. We look at the reasons here, and this is required for entanglement. Like we can't label them these two. They should be connected, but we shouldn't be labeling them using these properties. So yes, we look at the temporal walk-off. This is caused due to the difference in group velocities of the ordinary and extraordinary waves. This is the temporal difference. So one photon will come before the another. The spatial walk-off or the transverse walk-off is due to the pointing vector of the energy propagation direction being different from the optic axis. So that will again cause separation, spatial separation, which is uh, can be then the photons can be detected using detectors and beam splitters. Like I said, this is important for the production of entangled photons. So there won't be any information, and we can achieve pure entanglement from this, as we see in the applications. Last thing is that for SPDC, the conservation of momentum equation has an uncertainty to it, as should happen in quantum optics. Now let's look at the applications. This is the plot we did for the Selmar equations with the applications. The first application is to create a single photon source. This can be used to create single photon sources uh, in which you can localize a one photon state, so in which one photon can herald the coming of another. This is especially useful for communications. The signal is weak. This can be used to display quantum principles, proof of quantum principles, but the practical applications are not that much. So you can see the uh, after passing through the crystal, you can filter the extraordinary and ordinary part out, and this one of them can the idler photon can actually herald the coming of the how can I say of the signal photon. So that is another useful thing. Next, we can create indistinguishable photons, essentially. Uh, what we do is to show the indistinguishable nature of photons here, the bosonic nature of photons. This is evident in the fact that when the two photons created using SPDC exceeded the beam splitter from different ports, they engage in destructive interference, while when they came together from the beam splitter, they had a bunching effect and so had high probability of exceeding the beam splitter simultaneously. This shows the bosonic nature of photons. This is the experiment setup. Next, we move on to this application, entangled photon. Uh, this we this is used to show the entangled the nature of entangled photons, how we can create. So they used SPDC to create entangled photons in different polarization states. We use this to test Bell's inequalities using the procedure before we create uh, two photons, and we make intersections of the outputs of the twin photons with the different polarizations. So in this entangled state, we see that the photons are mixed in a way that if one is measured in horizontal and the other in vertical polarization, they'll be found in opposite polarization states. So this is the entangled state that we see, and this allowed us to violate the inequalities, and thus showing the extreme non-classical uh, nature of quantum entanglement.
Now we come to the final topic in this project, which is SPDC used in quantum technologies. Previously, we have seen that we can generate entangled photons using spontaneous parametric down conversion, and entanglement is one of the key features you need for the quantum technologies. And in order to actually bring the quantum technologies into practice, we'll obviously need to realize entangled qubits first. And since we are able to do that with photons, one would obviously like to use these photons for their quantum technologies. So now we'll see that how we can do that. So our first example is the quantum teleportation using SPDC. So quantum teleportation teleports a state uh, which contains the information, that is quantum information, from one place to another. It does not teleport the objects unlike shown in the science fiction movies. So the basic idea is that the sender, which is Alice, and the recipient, which is Bob, share an entangled pair given by 00 plus 1 by root 2. Here 0 1 can be basically the polarization of the light, 0 being the vertical, 1 being the horizontal, or vice versa. And they have a classical communication channel between them. And Alice also prepares a state alpha 0 plus beta 1, which she wants to teleport to Bob, and then she performs Bell state measurement on her qubits, and she sends that information to Bob by classical communication, that which Bell state measurement she performs, and according to that information, Bob performs some operation on his qubit, and he ends up getting the final state alpha 0 plus beta 1. Here I have shown the how the state evolves during this protocol, and first we apply C naught gate, which makes this state from psi 0 to psi 1, and then we apply Hadamard gate, which superimposes 0 and 1 in with equal amplitudes, and we can rewrite the state as this. And finally, after Alice makes her measurements, depending on if she gets 0 or 1, for the both qubits, she sends that information to Bob in form of M1 and M2. And finally, Bob performs the operations Z raised to M1 and X raised to M2 on his qubit. Here, Z raised to M1 basically means that he performs operation Z when M1 is 1, that is Alice's qubit collapse to state 1, and Z raised to 0 means he performs nothing. And finally, Bob ends up with the state alpha 0 plus beta 1. Now, this was a theoretical protocol, but how it was actually realized in 1997 at the University of Innsbruck is they basically used ultraviolet radiation pulse, and they passed it through a nonlinear crystal. A nonlinear crystal is necessary because SPDC is a nonlinear process, and it creates the entangled photons 2 and 3. And the photon 3 is then sent to the Bob, and the photon 2 is to the Alice. And when the retrorefracted ray travels through the nonlinear crystal again, it creates another pair of photons 1 and 4. This photon 1 is used by Alice to prepare her initial state, which she wants to send to Bob. And finally, she performs the base state measurement on her qubits, which are one and her photons, which are 1 and 2. And in order to do so, the first thing she needs to do is make the photons 1 and 2 indistinguishable, because that's the criteria for entanglement in photons. And in order to do so, she superimposes the photons 1 and 2 using a beam splitter. And this is basically done using the photon 4, the exact moment of time, as the photon 4 is used as the herald photon, which tells when the measurements need to be taken. And she sends that information to Bob via classical information channel, and he performs his measurement as we have discussed above in the theoretical protocol, and he finally ends up with the state alpha 0 plus beta 1. And we have, as we could see in the diagrams or the protocol, that the only thing that needed is Alice and Bob sharing an entangled pair, and they don't need any quantum communication channel between them. So this type of communication is very secure, as even if third party tries to interfere in some way, he cannot, because of entanglement is purely a global property and not a local property. The another example of this SPDC in quantum technologies is quantum cryptography. Here again we use the entangled photons generated by SPDC, which is 01 minus 10 by root 2, and these photons are sent to Alice and Bob via optical fibers, which is basically the quantum communication channel for the photons. And Alice and Bob make their measurements along different directions, so they measure the polarization along different directions, and they communicate these measurements over a classical communication channel. And if they match, they finally determine that the keys they have gotten the keys, and the communication between them is now secure. This is basically the quantum key distribution protocol by BB84 protocol. Now we finally come to the use of SPDC in quantum computation. Richard Feynman suggested using a quantum system to simulate another quantum system, where using a classical system uh, makes many problems like exponential scaling of the size of the system or the time needed. But obviously, realizing a quantum computer is no easy task. You need several conditions in order to realize a universal quantum computer. And one of the requirements is having a universal sets of gates. Universal sets of gates is basically a set of gates by using which you can perform all unitary operations in of any number of qubits. And C naught is one of those gate, along with the Hadamard and arbitrary qubit rotation gate. And E. Neil R. Laflamme and Milburn suggested a way to realize a C naught gate for photons in 2001, where they used SPDC. So here the basic idea is again, so having so your control qubits and a target qubit are encoded by a photon across a spatial mode, whereas in SPDC 0 and 1 corresponds to the polarization, but here it is spatial. So how first we need a polarizing beam splitter and a half wave plate, which makes the polarization encoded photonics qubit to spatially encoded qubits. And here the C0 basically means the state 0, C1 means state 1 of the control qubit, similarly for T0 and T1. And first we use a 50% reflective beam splitter, which for the target modes, which basically mixes the state 0 and 1. And after that, it's reflected here and here, and it also includes a one third reflective beam splitter. So as we can see, if the C1 is 1, then the control qubit or the target qubit which comes here interferes with the C1, and T1 becomes T0 and T0 becomes T1. So that's how the C0 happens. But when it's C0, the control qubit is 0, the target qubit doesn't face any interference, so it remains in the state as it was. So this was how the C0 gate was realized, although it was a probabilistic gate because of these beam splitters being one third and one third. So it was it gave the correct result in once in a 9 times. But it was the first step towards realizing an actual quantum computer. Of course, there are lots of many problems uh, in using SPDC or photonics qubits for quantum computers. One of them being uh, that SPDC can generate only a limited number of qubits at a time, and if you want to scale the system to a large size, you need to generate lots of entanglement at the same time, which SPDC cannot do. Although people are doing experiments for that and trying to implement the number of photons uh, generated at the same time, um, it was seen that it doesn't follow a Moore's law and it eventually reaches a plateau. So, and that number was somewhere around 32 qubits. Finally, the SPDC has applications in quantum metrology, for example, where the one of the example was given that the entanglement was used to perform a super resolution phase measurement, where the first prepared a known state given by n0 plus 0 n by root 2, and n is the occupancy of photons in that mode, and it was shown that the resolution given by this measurement was 1 by root n. And again, for the entanglement here, the SPDC was used. And another experiment, uh, this guy showed that the measurement of protein concentration can be done using entangled photons. Again, this guy showed that you can the, verify the violation of Bell inequalities using parametric fluorescence and entangled photons. And here, these guys showed that using SPDC, they